Okay, so it's May 20th. We've got our learning targets for today. And when we last left off, we had taken this solution of sodium hydroxide, 1.0 times 10 to the negative second molar, and we had computed the concentration of hydroxide ions, which was 1.0 times 10 to the negative second molar concentration of hydroxide ions. That's awesome. That's great. Congratulations. Yay. There's a catch. There's always a catch, isn't there?
There's almost 5 catches.
Well, do you remember what we said was the whole basis of the pH scale? It wasn't hydroxide. It's hydronium. It's hydronium. So we calculated the hydronium ion, or the hydroxide ion concentration of this solution. I'm just going to do that. And that's wonderful, and we should be congratulated and everything. But what we actually need to know is the hydroxide, or the hydronium concentration. Oops. Fortunately, algebra is our friend here. And do you remember what Kw is? Kw is the ionization constant of water. That's one answer. Kw's value is 1.0 times 10 to the negative 14th. Because Kw is equal to the concentration of hydronium and hydroxide ions. If we multiply those two things together, we get Kw. Well, that's fortunate, because for any aqueous solution at around room temperature, this has a value of 1.0 times 10 to the negative 14th molar squared. So that's mole squared over liter squared. Okay. Well, now we can use algebra. Since we know this and we know this, we can use this equation to solve for hydronium. That's pretty easy, don't you think? Okay, so we've rearranged to solve for hydronium concentration. We divide Kw by the concentration of hydroxide ions, and what do we get? 1.0 times 10 to the negative 12th. What are the units? Just molar, yeah, moles per liter or molar. And so this number is equal to our concentration of hydronium ions. Awesome! Now what? So first of all, let's just discuss, is this solution acidic or basic? It's basic. So the concentration of hydronium ions is less than that in neutral water. It's got a lower concentration of hydronium ions. This is a basic solution. And you kind of know that sodium hydroxide is a base. You would have expected that. Let's go ahead and we will do the calculations for computing both values for H2SO4. Let's do that together, okay? So that sodium hydroxide solution was a base. Okay, so given this solution, 1.0 times 10 to the negative 4th molar solution of H2SO4. This is relatively dilute. This is not a highly concentrated solution of sulfuric acid. Let's figure out the hydronium and hydroxide concentrations for this, okay? Now, first thing to know, is H2SO4 a strong acid or not? Yeah, which means it is going to completely 100% do what in water? Ionize. It's a molecular compound, it's going to ionize, and what is it going to form when it ionizes? Hydroxide or hydronium? Hydronium. So we're going to start with whatever it breaks down into, okay? We're always going to start with whatever this solution is going to produce. So let's do the ionization equation for H2SO4. Okay, so we've got the bones of the ionization equation. Are there any problems with this? Yes, there are. What's the problem? Not balanced. This has got 2 hydrogens in every molecule, and it's going to fully ionize. So we're going to produce 2 hydroniums, 2 moles of hydronium for every mole of H2SO4 that goes in, which means we're going to use up 2 moles of water for every 1 mole of H2SO4 that goes in. What's our next step? We can do a factor label now. So we know that we have 1.0 times 10 to the negative 4 moles of H2SO4 in every 1 liter of solution. And we know that for every 1 mole of H2SO4, we're going to generate, yeah, what?
2 moles of hydronium.
Bingo. 2 moles of hydronium ions. So what's our concentration of hydronium ions? 2.0 times 10 to the negative 4th molar concentration of hydronium ions. Okay. Pretty simple, pretty straightforward. Now, let's see, select all, copy, go to the next slide, paste, shrink, tiny, even tinier. That is really tiny. Okay. So we wanted to figure out the concentration of hydronium and hydroxide. We've got one of those two. What do we have to do to get the concentration of hydroxide? Kw, our old friend. So Kw equals hydroxide ion concentration times hydronium ion concentration. And we can solve for this because we have the other two. So Kw divided by hydronium yields hydroxide, or gives us hydroxide, rather. Okay, 1.0 times 10 to the negative 14th molar squared divided by 2.0 times 10 to the negative 4th molar gives us our hydroxide. Okay, so we divide that out. That's what we get, 5.0 times 10 to the negative 11th molar. These are pretty easy, right? You can calculate the concentration of hydroxide and hydronium ions. I'm going to give you some practice problems. I'm going to have you work until you finish those. Then we're going to go on to the next piece of this puzzle. Okay, we care about calculating hydronium especially because that's how we compute our pH. So pH is equal to, whoops, the negative of the log of the concentration of the hydronium ions. That sounds terrible, doesn't it? It's not that bad, I promise. So, how many of you have done logs in math? What is a log?
Power raised to the base of 10.
It's the power that you have to raise a number to, or the power that you have to raise 10 to get that number. Okay? So, it's kind of confusing, it's kind of weird. We're going to do the easy part of logs. This is not difficult log stuff. So if you haven't done logs, don't panic. Okay? Let's go back and think about our good old sodium hydroxide solution. And that was our, what, 1 point, whoops. That was a 1.0 times 10 to the negative 2nd molar sodium hydroxide. And we calculated the hydroxide concentration, and from that we got the hydronium ion concentration, and that was 1.0 times 10 to the what? Negative 12th. Okay, fantastic. Well, from this, if we have this number, if we have the hydronium ion concentration, we can calculate pH. So on your calculator, here's how you would enter it. I'm going to teach you how to enter it on the calculator, and then you're going to see how easy it is to enter it or to do it in your head. So on the calculator, you will press the negative sign, then you will press the button marked log. It's going to generate a parentheses for you, and then you just enter your value. So we would enter 1.0. There's a button that's 10 to the n, and then you would enter negative 1, 2, and if you use the plus arrow, or the arrow, you can push it over, close your parentheses, and then hit your equal or your enter button. Okay? I guess on our calculators it's actually an enter button. Okay, what do you get? 12. What do you notice?
Same as the exponent.
Huh, that's weird. As long as this number is 1.0, the absolute value of that is your pH. Okay? As long as this is 1.0 times 10 to the anything, this number's absolute value is going to be your pH. That's fantastically easy. So, pH is the absolute value of the exponent from the number in the scientific notation that shows the concentration of hydrogen. The big asterisk here is as long as that number n times 10 to the x, as long as this equals 1.0. Okay? As long as that is 1.0, all you have to do is take the absolute value of that. Okay? And there's a nice little chart in your book on page 485 that shows the relationship between hydronium ion concentration and pH. I reprinted a different chart that I found online. It's not quite as lovely, but it gives you the idea that the higher the concentration of hydronium ions, the more acidic we consider something. And every step up of 1 in pH is a step up of 10 times. So, and remember, we're talking about at room temperature. We're talking about here at room temperature because remember, what happens as we increase temperature? Ionization increases. Yeah, the self-ionization of water increases. So here we're talking about at a range of temperatures that are reasonably room temperatures, hovering around 25. Most aqueous solutions are going to have a pH between 0 and 14. What does that mean? It means that the concentration of hydronium ions of most substances at room temperature is going to be greater than 1.0 times 10 to the 0, or 1. And it's going to be less than 1.0 times 10 to the negative 14. Did I reverse that?
Yeah.
I did. There we go. That's better. We'll fix that. So it's gonna there's going to be more hydronium than 1.0 times 10 to the negative 14th, and less than a concentration of 1 mole of hydronium ions per liter. So that's, and anything that falls on, so this neutral ground is 1.0 times 10 to the what?
-7.
Negative 7th. So anything that's over here is a base. Anything that's over here is an acid. Okay? And anything that's right in this territory is neither base nor acid. It's neutral. So these are pHs from 14 down to just above 7, and these are from just below 7 down to a pH of 0.
Is it water of 7?
Pure water is a 7, yes. Pure water is a 7. And there are other compounds that are 7s. Salt water, sodium chloride in water is neutral, because the substance sodium chloride does not contribute anything that's going to accept or donate protons. It's not going to force the water to create more hydronium or more hydroxide ions. So a saltwater solution is still going to be neutral. So there are lots of things that are pretty neutral in that. Does that sound reasonable?
Yes.
Wunderbar. We'll do one of these together, and then I will go ahead and turn you loose on 16, 17, and 18 to do. I'll let you get at least one of each of those done, and then we'll go on to the more difficult cases. So let's do number 1, part A on 487. Okay, we've been given a 1 times 10 to the negative 5th molar solution of nitric acid. So the first thing we want to figure out is what? Does it dissociate? Does it ionize? How many moles of hydronium or hydroxide are we going to get out of this per mole put in? And what's your answer? So we've got our ionization and we've got our mole ratio. Now we look at the concentration overall, and from that we can determine the concentration of hydronium. Okay, if we're just calculating pH and we have the concentration of hydronium, do we have to find the concentration of hydroxide? No. We need hydronium. We've got hydronium. So based on this, because it's a 1.0 times 10 to the something, we can just say that the pH is going to be what?
5.
pH equals 5. So this is mildly acidic. This is a pretty dilute solution of nitric acid. It's still a strong acid, but it's a dilute solution. Pardon? I wouldn't play around with it either. So if we were entering this in the calculator, we would do what? Negative log 1.0 times 10 to the negative 5th, close parentheses, and that would give us an answer of 5.
On purpose.
All right. Obviously, if you were given one like sodium hydroxide or potassium hydroxide where it generated hydroxide ions, you would have to use Kw equals and algebraically solve for hydronium. I'll let you get started on numbers 16, 17, and 18. Get at least all parts A and C, and then we'll take the more difficult case and we'll work so you can work on number 19. Obviously, and I think there's one of your homework problems that does this. If we give you the pH, can you find the hydronium ions? Yes, and there's a way to do it on your calculator. We're not going to spend a whole lot of time on that because I'm more concerned with you being able to calculate the pH, but we'll look at that a little bit later. Okay, so if we have a weak acid like acetic acid or phosphoric acid or hydrofluoric acid, we can't calculate its pH. We can measure its pH with a strip, but we can't calculate it. Why not?
Does it ionize fully? Because not all of it ionizes.
It's not all of it ionizes, and we have no way of knowing at any given moment how much is ionized. So we don't know at any given point in time where this equilibrium is. So we can't calculate it. We can measure the pH and we can back figure to see how much of it is ionized in a moment, but we're not going to do that. So we're not really going to focus on that, but you should be aware that that can be done. Inquiring minds want to know. You've wanted to know. You've been kept awake at night wondering what pH stands for. Pouvoir hydrogène. It is French. Yes, it is French for hydrogen power. Hydrogen power! So you can get a cape, and you can go as Captain Hydrogen for Halloween next year with a wand that transforms people into naked protons. You will be the life of the party. So it's the negative log of the concentration of hydronium ions. It's the hydrogen power. They're negative, the French? I'm lousy at French. Pouvoir hydrogène? I don't know. That's as good as it gets. Okay, now, there is also POH, which you have never heard of, correct? Nor are you ever going to hear of it again. It's hydroxide power. Yeah, so you've got hydrogen power and hydroxide power. It's like the hero and the villain, the hero and the anti-hero. You could go with your best friend for Halloween next year, take your little siblings and make them naked protons, and it's a great party for everybody. You don't think that...
No, once you,
Okay, so calculating pH step by step. No matter what you are given, you can calculate the pH of a strong acid or a strong base. And there are two rundowns here. Because the first question you're going to ask yourself is, does this generate hydronium or hydroxide? Okay? If it generates hydronium, find the concentration of the solution. That's usually given to you. 1.0 times 10 to the negative second molar. 1.3 times 10 to the negative first molar, whatever. Write an ionization or dissociation equation. Really, you're just trying to figure out what the mole ratio is between the solution and the ions you're interested in. And then you're going to factor label to figure out, in this case, what the concentration of hydronium ions is. Once you've got that, look at the power of 10. As long as it's a 1.0, you've got it. If not, you have to do a little work on the calculator. For things that generate hydroxide, there's one extra step. What is it? Using the constant, using kW. So here you do all the same things you do for something that generates hydronium. Find the concentration, again, it's usually given. Write an ionization or dissociation. Factor label to find the moles of hydroxide. But then you're going to use K equals hydronium times hydroxide to solve for hydronium. Once you've got that, it's the same simple thing. So, what if we have something that has a concentration of hydronium ions like that? I'm going to tell you that 3 is not the pH here. What do we have to do? Got to use your calculator, and you're going to enter the following sequence of buttons. Okay, so you're going to hit negative log. It'll pop up some parentheses for you. Enter 2.5. Use the 10 to the n button. Enter your power. If you're using the school calculators, you then have to use the little arrow key to allow you to close the parentheses. Close the parentheses and hit your enter or your equals button. And what do you get? Okay, so that gives you a pH of 2.6. You can do this for any of them. It's really pretty darn easy using this calculator or using a calculator in general. Questions, comments, concerns? You got time to practice.